Hey guys, it's Brandon, and we're just going to quickly review oscillations and waves in this little snippet here. You'll remember that an oscillation is just motion that repeats itself over and over and over again. And so to characterize oscillations, there's a couple of different things we use to describe it. The first is the period of the oscillation, t, and this is the amount of time to complete one full motion. To complete one full motion, we'll call it one repeat if you like of the behavior. And we also talked about frequency, which is how many times in 1 second it takes, how many oscillations can you get in 1 second. And period and frequency are of an inverse relationship, as you'll remember. So we talked about this in two contexts. One was the box and spring, and the other one was the pendulum. You remember that the box and spring, we had a spring attached to a box of mass m, and the period for a spring attached to a box is 2 pi times the square root of the mass attached to the spring divided by the spring constant. So this is the period. And the application we used here was astronauts weighing astronauts in space. If you attached an astronaut to a spring, you'd find out what their mass is by just measuring the period of oscillation if you knew what the spring constant was. So this is the application we thought about. Then we talked about pendulums. I'm not sure what the proper plural is of pendulums, but we're going to go with that. And here we have a pendulum. It's swinging, and you'll remember that the period of oscillation for a pendulum is related to the length and the acceleration from gravity. So what's surprising here is that m is not in the equation. So regardless of how much mass is attached to the end, it will swing at the same rate. It'll complete the motion in the same amount of time, provided that the length of the pendulum is the same. So this is the property of pendulums that Galileo was fascinated by. Okay, so there's a couple of ways we can characterize the oscillatory motion. One is this, if I were to draw, say, a position versus time plot here. Oscillatory motion is like a sine wave or a cosine wave, and one full repeat of the motion, this would be the period t. The maximum displacement from equilibrium is the amplitude a, which is also a way to characterize, this is the energy, if you like, one way to characterize how much energy is in the oscillation. And all that an oscillation is a trade-off between potential and kinetic energy. So when a pendulum is on the far side of a swing, all the energy is in potential energy. When it's in the middle of its swing, it's moving the fastest, and it has no potential energy anymore. All of its energy is in kinetic. And then on the far side of the swing again, it's all potential again. So it's just this continual exchange between the two. So that's all as much as we're going to talk about oscillations. Remember that pendulums have this interesting property that there is an independence with mass, and that will be something that you'll see tests exploit again and again and again. So I'm going to put a little divider here in my notes, and we're going to talk about waves and a little bit of a change of pace here. So if I send a disturbance through a medium, a small one and a big one, the wave speed, the speed at which the disturbance will propagate through the medium is independent of that. Both waves would travel at the same rate. So we say that the wave speed, and I'm going to call that c because kind of after the speed of light here, but it could be any type of wave. It depends only on the medium, properties of the medium. So the example that we use is waves on a string. We know that the velocity of waves on a string is equal to the square root of the tension on the string divided by the linear mass density. There's nothing in here that says anything about amplitude. A is not there. So what that means is small disturbances travel just as fast as big disturbances. For sine waves, we talk about the fundamental relation for sine waves And I'm going to say that the velocity is, we'll call this the wave speed here, even though I'm being inconsistent. Here is the wavelength. And here is the frequency of the wave. So if I know what the wave speed is and I have the wavelength, it's somewhat trivial to back out what the frequency of that wave would be. Wavelengths, as you'll remember, if I again draw another sinusoidal plot here, this time instead of being a plot of time versus position, it's position versus position. This is what the wave physically looks like. The distance between crests is the wavelength. And again, this distance here is called the amplitude. The maximal displacement from equilibrium is the amplitude again. Okay. So waves are cool because they can interfere with each other. What that means is if I have one big wave and it's moving this way, and I have another wave that's moving this way, when they pass through each other for a minute, you'll get a wave that's really big. Conversely, if I have one wave moving this way and say a trough moving to meet it, then the moment they pass through each other, the two waves will cancel out. Particles don't do this. Waves are just, waves allow for interference. So if waves can interfere, there's certain types of waves that can form in objects that we call standing waves, which are interference which is self-sustaining based on the rate at which energy is being injected into the system. So you remember that in class we talked about a child swinging on a swing. There's certain points along that swing at which we would give pushes to the child and the child would start swinging higher and higher. That's a standing wave. If we apply pushes at random intervals along the swing, in fact, all those individual kicks and pushes would cancel out and there wouldn't be any wave-like motion in the long term. And so we talk about these things called standing waves, which is where energy is being injected at this rate. So the application that we looked at was pipes, if you'll remember, and we talked about open pipes, and I'm going to call these open or closed. Either way, the math is the same. And we were drawing pictures like this, which shows the waveform inside of the pipe, say as a standing wave is created. These little dots here are called nodes, and the crests here are called antinodes. So let's say that I knew the length L of the pipe, and I wanted to be able to calculate what the wavelength is for a given vibrational mode of the pipe. Then we know that lambda for an open or closed pipe is equal to twice the length divided by the mode number. This is not mass. This is mode number. Okay. So for the fundamental mode, the wavelength is twice the length of the pipe. We also talked about clopen pipes that are open and closed, and we were drawing things like this. This is the m equals 3 mode that I've just happened to draw here. We'll call this L. Its wavelength is given by 4L divided by m, where m is odd. So the second vibrational mode is the m equals 3 mode, which seems like a contradiction in terms, but that's just to make the math work out. We restrict m to being odd numbers. So let's say that I wanted to find the frequency, though. I know what the wavelength is. I want to find the frequency. We would combine lambda equals 2L divided by m, or 4L divided by m, as the case may be, with v equals lambda times frequency. And you would get that the frequency for open or closed pipes is mv divided by 2L. This is for open or closed. And frequency for the second case, which is the clopen pipes. Again, m is odd. But all we did, these new formulas that I'm underlining right here, are just what happened if you combine the fundamental equation for sinusoidal waves with either of these equations here. Okay. All right. Well, what can you do with waves? So after this, we began talking about the Doppler effect and the decibel scale. So you'll remember that the Doppler effect is the siren effect. If you start out at really, if you hear a frequency coming from a source that's approaching towards, which is approaching you, then you expect the pitch that you would hear with your ears to be higher, and that's the Doppler effect. So we'll say approaching sources seem to have a higher pitch. So there's a formula for taking care of this, and what it is the new frequency we say is equal to whatever the sound speed is, which in this class is 343 meters per second, or if you're taking a standardized test, you round that to 350 to make the math easier on yourself, plus or minus the velocity of the receiver, divided by c minus or plus the velocity of the source. We'll multiply that by the original frequency. Okay, this is the new frequency. So there's a way to calculate it, but you should know for certain that if a source is moving away from you, the pitch will sound lower, and if it's moving towards you, the pitch will sound higher. That's the basics of the Doppler effect. And by the way, I believe that's the way an ultrasound works as well, is just using the Doppler effect to do mapping and imaging. Okay, so that's the Doppler effect. How do you choose pluses and minuses? You choose them based on whether you believe that frequency should be higher or lower based on whether the source or the person receiving the signal is moving away from or towards the source in question. I'm not going to cover that in this video. There is a great Wikipedia article on how to do it, but honestly right now it's not that important. So just kind of remember qualitatively what the Doppler effect is supposed to be talking about. The next important concept was the decibel scale. This is kind of important here. The decibel scale is a way of describing the intensity of a sound that sort of agrees with our ears. So you'll remember there's this thing called Weber's law or something like that, which says that a tenfold increase in stimulus results in a twofold increase in sensation. And so a sound that sounds 10 times as intense is actually only perceived by the ear as being like twice as loud as the general idea. Basically, it's a sophisticated way of saying your ears have a logarithmic response to signals. So you'll remember that the decibel scale had this log formula to it. So this is the intensity in decibels, if you like. And it's equal to 10 times the log base 10 of whatever the intensity you're dealing with divided by the reference intensity. I naught is 10 raised to the negative 12 watts per square meter. This is the threshold of hearing. So that we kind of have a baseline. Okay. All right. So there's a couple of little questions we can ask you about the decibel scale, which are kind of important. The first is that if I have maybe, I don't know if this is a good way to say it, let's say that I have 10 sources of sound and they are each 40 decibels. How loud is the sound from all? So one of the things we might be tempted to do, this is the wrong way to do it, I'm going to put a skull and crossbones here, because you're not supposed to do it. Frowny faces, I don't know how else to incentivize it, is to just go 10 times 40 decibels equals 400 decibels. And that's ridiculous. That's not the way the decibel scale works. The decibel scale works by saying that a 10-point increase in decibel means intensity has increased by a factor of 10. So, for example, if I were to ask you, you have an 80 decibel sound and a 60 decibel sound, how do they compare in loudness? Well, there is a 20-point difference between the two of those. And so if there's a 20-point difference, that's two 10-point differences. Each 10-point difference is a factor of 10. And so this is 100 times louder than the 60 decibel sound. So it kind of gives you a way of sort of containing and controlling sounds there. So again, going back up to this example here, you might wonder what's the correct way to do that. We have 10 40 decibel sounds. Well, it wouldn't be 400 decibels. Remember that this is in log space and we can't just multiply things together. What decibel reading is 10 times as powerful as a 40 decibel sound? Well, the definition of the decibel scale is that's a 10-point difference. And so really, if we wanted to do this problem, it'd actually be 50 decibels. 50 decibels is 10 times louder than 40 decibels. So there you go. Or more intense, maybe, is the best way to say that. Remember that intensity is just the power divided by 4 pi r squared, where r is the distance from the source. And if we want to compare intensities at different radii, say you have someone at 100 meters listening to a sound versus someone at 1,000, and you want to know how the intensity falls off, you can use this formula here and rewrite it for two different intensities and two different radii in this way. And I did write this here correct. So there's a proportion that you can kind of run to do that. But in general, this is an inverse square law. So if I move back by a factor of 2, the power, or the intensity as I perceive it, falls off by a factor of 4. So it falls off rapidly. There's an inverse square law in operation there. Okay, well that's actually all the content, a very brief crash course of it for waves and oscillations. So I'm going to stop the video there, okay? See you next time.